Don't be a backseat problem solver.
Hi everyone, it's Virginia here, and now we're going to go through quantitative acid basics. So go ahead and grab your calculators and some paper, and make sure you're working through these problems along with me. My email is there at the bottom in case you want to get in touch. So let's go ahead and get into it. We're going to start by working with HClO4. And we know from having memorized our strong acids and strong bases that this is, in fact, a strong acid. And so they're asking, when we have 500 milliliters of a 0.8 molar HClO4 solution, what is the H plus concentration? So we can go ahead and write the dissociation of HClO4. And because we know this is a strong acid, we know that it's going to completely dissociate and break apart 100% into protons and perchlorate ions. And since the protons and the perchlorate are present in a 1-to-1 ratio, we know that our concentration of H plus then is just going to be equal to our concentration initially of the HClO4, which is going to be equal to that 0.8 molar. So they did give us a volume, but we don't need our volume when we're thinking in terms of concentration. If I have a half gallon of Death by Chocolate, or if I have a cone of Death by Chocolate, it still has the same concentration of chocolate chips and stuff within it. It doesn't change what it is just by being present in a different amount. Okay, so then they go on to ask us to figure out the pH of the solution. And we know that pH is the negative log of our proton concentration, which is going to be the negative log of 0.8. And this value ends up being about 0.1. So this is a very acidic solution, which is expected. And so then they go on to ask what the pOH of the solution would be. And so we know that pKw is equal to pH plus pOH. And at 25 degrees Celsius, or 298 Kelvin, that number is 14. pKw is 14. So we can use that and say 14 minus my pH, which is the 0.1, will be equal to my pOH, which is going to be 13.9. So from that, they want us to figure out what the hydroxide concentration of the solution is. And so we kind of have to undo that P. We have to undo the negative log. And so if we think about pOH being equal to the negative log of hydroxide concentration, we can rearrange this to solve for hydroxide concentration. So what I'm going to do is move the negative sign to the other side. And then to undo the log, I'm going to do 10 to the power of both of those things. That will cancel my log base 10 and just leave us with hydroxide concentration. So we'll have 10 to the negative pOH, which in this case is 10 to the negative 13.9, will be equal to my hydroxide concentration. And when we plug this in, we get 1.26 times 10 to the negative 14 molar. So we have a really, really tiny amount of hydroxide present in the solution, which makes sense because it's a solution of a strong acid. And you can use the 10 to the negative pOH strategy to also undo the negative log of pH, maybe. So if you want proton concentration, you can do 10 to the negative pH. Okay, so now, instead of having a strong acid, we have a weak acid, benzoic acid. So it's not going to completely dissociate. There's going to be some equilibrium, which is represented by this KEQ number that they've provided. So the first step is to write the reactions that are associated, and we can write for acids the reactions in two different ways, and it works out the same. So we have kind of the shorter, quicker way to write it out, where we just have our acid and it's in equilibrium with its conjugate. And the dissociated protons. Or you can write this with the water that's also present in solution. And both are equally correct in terms of the problem solving. So if you like including the water every time, go ahead and do that, because in some cases you do always have to have it. And we'll look at that in a minute. But in this case, we still have our conjugate present, but then instead of having protons present, we're going to have hydronium, or H3O+. And we can treat these as being synonymous. One's just connected to water and one is not, and that's fine. Okay, so now we want to find the pH of a 300 milliliter solution of this benzoic acid that's present at 0.035 molar. So let's go ahead, and I'm just going to use the shorthand equation that we wrote above. And so when they're asking us for pH, what they really want us to figure out is the equilibrium concentration of those protons. And so to figure out equilibrium concentrations, given a K, we're going to go ahead and use nice table. And so what we want to figure out is this value. And then once we know our proton concentration, it's simple enough to go to pH. So for my initial benzoic acid, I'm going to use the concentration and molarity that's given. We always use molarity in ice tables. And I'll have 0 of these to begin. And so we're going to add to the side where we have nothing. And subtract from the side that we actually do have something. And so for our equilibrium value, the benzoate, the value is just going to be X. And for the protons, it's just going to be X. And so now it's time to use our Ka value to solve for X. So we know our Ka is going to be our aqueous products over our aqueous reactants. And they've given us this value above. So that's 6.5 times 10 to the negative 5. And so we can set this equal to x squared over 0.035 minus x. And so as it's written now, we would need the quadratic equation to solve for x. But if you look at our k value, we have a really small number. It's 10 to the minus 5. And so if we did use the quadratic equation, we would get a pH that'd be very similar to the number we get if we ignore any x's that are added or subtracted. And so we say this number would be negligible, so we're just going to go ahead and ignore it. And that makes solving this really easy now. We can just multiply over by 0.035. And we end up saying that 2.275 times 10 to the negative 6 is equal to x squared. And then we can take the square root to find x, and x ends up being 1.51 times 10 to the minus 3 molar. And so if I look up at the table to figure out what that number is actually corresponding to, it's corresponding to my proton concentration. So this is molar protons. And we can write that up on our table also. And so we have proton concentration, so if we want to get to pH, we just go ahead and say pH is going to be equal to the negative log of 1.51 times 10 to the negative 3, which gives us a pH of 2.82. And so that would be our final answer. And we can do a check when we have a pH we feel like we're ready to bubble into our Scantron. And say, okay, I started with an acid, so I know my pH that I get should be less than 7. And this number is, so we can do our last check and say that this number makes sense. So now this problem is similar to the previous one, except now instead of starting with benzoic acid, we're starting with the conjugate salt here. So to start, we want to think about how that salt is going to dissociate in water. So we'll have how it begins, and then in water, we'll say it's a strong electrolyte, so it's going to completely dissociate, break apart 100%, into the C6H5 COO- and the sodium ions that it was paired with. And so we know sodium's a spectator, so we're not worried about it. It'll still be in solution, it's just not going to participate in the reaction. And so we're left with our conjugate of the benzoic acid. So the conjugate of a weak acid is going to be a weak base. So in this next step, when it asks what reaction is going to occur, we're going to write a base hydrolysis reaction. We can start with our conjugate. And in this case, we do have to include water in our reaction. And that will be our source of protons. So our C6H5COO- is going to take a proton from the water to form the neutral solution, or the neutral species, in terms of charge. And it will leave behind hydroxide. So this is a base hydrolysis. So the equilibrium constant we need is a Kb, B for base. But In this problem, they don't give us a Kb. What they gave us in the last problem was the Ka for the benzoic acid. So they gave us the Ka for its conjugate. And so when we need to convert between Kas and Kbs of two conjugates, we can use the relationship that Kw is equal to Ka times Kb. And so at 25 degrees Celsius, go ahead and say that Kw is 1 times 10 to the negative 14. And so that will be equal to our Ka times Kb. And so with some simple division, we can figure out that Kb then is equal to 1.54 times 10 to the negative 10. Okay, so then to figure out the pH of the solution, we ultimately want to figure out our proton concentration, but we don't have any protons in this equation. Well, that's okay because we do have hydroxide in the solution, and we can use the relationships between hydroxide concentration and proton concentration to figure out our pH. And so to do this, we're again going to have to set up an ice table. Okay, so now we have our ice table set up with our base hydrolysis reaction. And what we're going to solve for here is our equilibrium concentration of hydroxide. And we'll use our Kb to do that, and our Kb expression is going to be equal to our aqueous products over our aqueous reactants. So we're not going to include water in this expression. We're going to treat it as if its concentration is 1. Okay, so we can plug in our initial values. So we have 0.75 molar of the benzoate. We're not going to worry about water in our ice table because it's a liquid. And we have 0 to begin with for the hydroxide and the benzoic acid. And we'll add 1x to those sides and have x as their equilibrium values. And we'll subtract from the left side. And so then we'll take our equilibrium row and we'll plug it into our Kb expression. And so as our Kb expression is set up now, our Kb is really small. It's less than 10 to the minus 5. So we can go ahead and ignore added or subtracted x's. And then solving this becomes simple again because we can multiply the 0.75 over and then eventually take the square root to solve for x. 1.15 times 10 to the minus 10 is equal to x squared. Take the square root and we find that x is equal to 1.07 times 10 to the minus 5 molar. And so we want to look up at our table and figure out what the x is actually corresponding to. And it's corresponding to our hydroxide concentration. And so when we take the negative log of this value, we won't have pH. We'll end up solving for is pOH. So when we do the negative log of 1.07 times 10 to the negative 5, we get a pOH of about 4.97. And so we'll use our relationship with pKw again to say pKw is equal to pH plus pOH. And at 25 degrees Celsius, this number is 14. So we can just do 14 minus our 4.97 to get our pH. That pH ends up being 9.03. So we can then, do our check with what we started with. And we know we started with a conjugate base. And so we should have a pH that's greater than 7. And so this makes sense. So speaking of conjugates, we have here some fill in the blank. So the conjugate base of a strong acid is actually going to be such a pathetically bad base that we say it's not going to do anything. It's just going to be a spectator. And so we would say maybe that they're neutral in terms of their impact on pH, or maybe that they're negligible. Okay, but the conjugate of a weak acid is also going to be weak, but it's going to be a weak base. And the conjugate of a weak base then is going to be a weak acid. So any group 1 metal cations and the group 2 metal cations below are going to be spectators, because if we were to pair them with hydroxide, like NaOH, we would have a strong base. So the sodium ion that it would dissociate into is going to be a negligible acid, or spectator, or neutral. So some things can be acidic or basic. So it can act as both an acid or base. We call these amphoteric. So the prefix amph means both. So you can think like amphibian. And some examples of this are, water, or something like HCO3 minus, because we have here a proton that it could donate, but it has a negative charge, which suggests that it wouldn't mind acting as a base and picking up a proton from the surroundings. And so now we have the gauntlet, where we have a bunch of salts, and we want to figure out, when we dissolve these in water, what would happen to the pH? Would they be basic and increase the pH, neutral and not change the pH, or acidic and drop the pH? And so at this point, I want you to stop and ask yourself, do I really know my strong acids and bases? If you feel like you can use some refreshing on it, take a minute and make some flashcards and make sure you learn your strong acids and strong bases, because that will make this process a lot more straightforward. Okay, but if you're ready, let's get into it. Okay, so our first step when we want to figure out if a salt is acidic or basic is to think about what it's going to dissociate into in water. So for our first salt, NaCl, will dissociate into sodium ions and chloride ions. And so we have to think, what would these be the conjugates of? And sodium would be the conjugate of sodium hydroxide, strong base. So this is going to be neutral. We're a spectator. And chloride is the conjugate, or would come from HCl, which is a strong acid. So this would also be a spectator. So this would be a neutral salt. So next to it, I'm just going to write equals 7, because the pH would stay at 7 when dissolved in water. Okay, so next up we have NaF. So this will dissociate again into sodium ions. Then instead we'll have fluoride ions. So sodium, we've already said, is going to be neutral. Fluoride would come from HF, which is a weak acid. So this ion is going to be a weak base. So overall, this salt would be basic. And our pH would end up being greater than 7 after dissolving this in water. Okay, and we have potassium sulfite. So we'll end up dissociating into 2 K+ ions and 1 SO3 2-. So potassium would come from potassium hydroxide, KOH, which is a strong base. So this is going to be neutral. And then sulfite come from H2SO3, which is a weak acid. So this is going to be a weak base. And so this salt overall would also be basic. And the pH would be greater than 7 when we dissolve it in water. Okay, next up we have iron chloride. So this is going to dissolve and form iron 3+ and 3 Cl-. Cl-, we already said, comes from HCl, which is a strong acid. So this is going to be neutral. And then we're left with iron 3+. We have a small, really positively charged species. So this is going to be a good Lewis acid. It's going to be really good at accepting electron density from something like water, which would then hydrolyze the water and release protons into solution. And it's actually pretty good at doing that too. And so our pH is going to be much less than 7. Okay, so now we have calcium iodide. We'll end up with the calcium ion and 2 iodide ions. So calcium we can think of as being related to calcium hydroxide, which is a strong base. So calcium ions will be neutral. And iodide would come from HI, which is our friendliest of acids and is also a strong acid. So iodide ions are also neutral. So our pH would remain at 7. Okay, here we have lithium chloride dissolved to give us Li+ and ClO2-. Li+ we can think of as being related to LiOH, which is a strong base. So the lithium ions are going to be neutral. And this chloride ion would have come from HClO2, which is a weak acid. So this is going to be a weak base. And this salt will be overall basic. And our pH will end up being greater than 7. For one of my favorite salts, rubidium bromide, it's going to dissolve into Rb+ and Br-. Rb is connected to RbOH, which is a strong base. So this will be neutral. And Br- would come from HBr, which is a strong acid. So this will also be neutral. Okay, here we have lithium chlorate. We'll dissociate into Li+ and ClO3-. As we said before, lithium will be neutral. So it's associated with a strong acid, LiOH. then the ClO3 minus would be related to HClO3, which is a strong acid, so this will also be neutral. Okay, next up we have Chakuk, also known as potassium acetate. This will dissolve to give us CH3COO minus and K plus. As we said before, potassium ions would be associated with potassium hydroxide, strong base, so this will be neutral. And the acetate ion would come from acetic acid, which is a weak acid, so this will be a weak base, and the pH will be greater than 7 after dissolving it. So now we have ammonium iodide, which will dissociate into NH4 plus and I minus. So we said before iodide, so this comes from a strong acid, so this will be neutral. And NH4 plus, you could think of it as being the conjugate of ammonia, NH3, which we know is a base. Or you can say that if we have a nitrogen, a hydrogen, and a positive charge, that's a good sign that something will be a weak acid. So any nitrogen with 4 bonds and a hydrogen has the potential to donate that hydrogen into solution. So this salt would be acidic, and our pH would be less than 7. Okay, so now we have NaBrO. The sodium will dissociate off on its own, leaving behind the covalently linked BrO minus. Sodium ions we know are spectators, so this will be neutral. And the BrO minus would come from HBrO minus, which is not one of our strong acids, so it must come from a weak acid, making this a weak base. And this salt will overall be basic. And the pH will be greater than 7. Okay, and then we have this compound, which might look a little intimidating, but what I see here is this part staying together and the iodide dissociating off to be I minus. Which we know is a spectator, so the I minus will be neutral. And the CH3 NH3 plus, we have a nitrogen hydrogen positive charge, so this will be a weak acid. We have a nitrogen with 4 bonds and a hydrogen that it can give up. So this salt will be acidic. And so now we have K2O. This one's a little strange because it's a metal oxide. So when we have something that just ends in oxygen like that, it's going to be an oxide. And our metal oxides will be basic. And so if we were to put this K2O in water, it would eventually react to make KOH, which we know is a strong base, so it's going to be basic. With the Al2O3, now we have a metalloid oxide, and these will be amphoteric. They can be acidic or basic. Which makes sense because metalloids are kind of sitting in the middle. Oops. And then here now we have a non-metal oxide. And these will be acidic. You can think this will eventually react with water to become HNO3, which we recognize as a strong acid. So it makes sense that they would be acidic. Okay, that's it from me for now. Good luck. Keep up the hard work. You're doing great. And you can make it through this chapter and finish it strong. Okay, I'll talk to you later.